we are going to learn how to convert from mass to moles, but first we have to understand how to calculate what's called a formula weight and a molar mass. This video is especially important because if you think about when you're working in the lab, and let's just pretend that I was to say that we needed to use 3 moles of a compound. Okay, well, that's not really doing you any good as far as in the lab, because you're going to need to know what that is in grams so that you can put that on a balance and get the mass, right? So, and actually measure it out. Okay, and so it's a common practice that we need to be able to convert between grams and moles. Okay, but first we want to look at how to calculate a formula weight or a molar mass of a compound. And basically what you do is, if you're given, I may have gone too far. Nope, I'm good. Sorry about that. Okay, so the formula weight is the sum of the atomic weights. So if you look at your periodic table, it's that number underneath the element. That's some longer number with a few decimal places after it. Okay, you're going to sum up the atomic weights of all the atoms in the compound. And if you use the term formula weight, that means you report your answers in AMU. That just means atomic mass unit. So if you had, here we have iron sulfate. Okay, it'd be iron and iron 2 sulfate. We have, look at it, we have 1 iron, 1 sulfur, and 4 oxygen atoms. So to calculate the formula weight, okay, we're going to take that 1 iron atom and we're going to use the periodic table, and its atomic mass, atomic weight is 55.85. Okay, roughly, some periodic tables may go out another decimal place or whatever, but around that. You have 1 sulfur atom, so it has a mass of 32.07 atomic weight, and you have 4 oxygens, so you're going to take 4 times 16, because 16 is the atomic weight of oxygen, and then you add those up. 55.85 plus 32.07 plus 64.00 gives you a formula weight of 151.92. Okay, our unit here is AMU. A more useful unit for us is what we call molar mass, okay? Because the periodic table is all based upon 1 mole, and we've established that in previous lectures, then we can add up the molar mass of a molecule or a compound the same way, but instead we can report our answer in grams per mole. Okay, so that's our new unit here. So the only thing that's changing is our unit. Okay, so the carbon's atomic weight is in AMUs. That's the unit. But if you look at the molar mass, we know that carbon is based upon 1 mole, because every element is based on 1 mole. Okay, that's the commonality of our periodic table. So the molar mass, the value of your molar mass, okay, is equal to the formula weight. Okay, the only thing that we're changing are the units. So you add up you take each element and multiply it times how many you have in the formula. Okay, and then the molar mass relates the moles to the grams, and this is super important for us, and this is used as a common conversion factor. So here we go, we've got another conversion factor. Okay, previous video, our conversion factor was 1 mole is equal to Avogadro's number. Here you can add up the molar mass of an element, compound, whatever, and that number is equal to in the units of grams per mole. So if you look at hydrogen, it has an atomic weight of 1.01, and you have 2 of them. So you got 1.01 times 2. I'll write this out just so you see it. So if we did H2O here, okay, we have 2 hydrogens. 1 oxygen. That looks like 10, so oxygen, just 1, times 16 is its atomic weight. And so if we add those together, we get 18.02. Okay, so that was in formula weight, we would write out AMU. But what we're changing here, the only thing we're changing, is that's the same thing as saying 18.02 grams per mole. And this will be very important to us. Okay, and so you can actually write conversion factors that look like this. For every 1 mole, there are 18.02 grams of water, or you could flip it over. These are the same. 18.02 grams for every 1 mole of water. Okay, so we can do this for all of our compounds and elements. All right, and so these now can be plugged into conversion factors and can be used in our equations. Okay, so let's see how we could do this. How many moles are present in 100 grams of aspirin? Okay, aspirin has a formula of C9H8O4. So pretend that when you're on your own, you weren't given the 180.2, because technically you should be able to add that up yourself. So if you take 9 carbons times its atomic weight, which is 12.01, and you take 8 hydrogens times its atomic weight, 1.01, and you take 4 oxygens times 16, which is the atomic weight of oxygen, you should get 180.2 grams per mole. Okay, molar mass means our unit is grams per mole. Okay, so I always say to write out what you know first. Okay, we have 100 grams of aspirin, so that's C9H8O4, and I want to convert, but all I know right now is I need to get set up correctly. If I have grams in my starting number, I have to have grams in the denominator here for these to cancel. Okay, and so now the question is, what do I plug in? What do I have? What are my common conversion factors, common units that could fit in here and give me what I want? Because I want mole of aspirin. All right, so aspirin, if we look at our conversion factors, has a molar mass of 180.2 grams per mole, or we could flip that over and plug it in as 1 mole per 180.2 grams of aspirin. So if we think about what I wrote out earlier, mine went blank on how many hydrogens I had. That's what I was going to put. 4. Okay. So if you look at what we wrote out, think about it. If I plug in this, moles is going to be in the denominator, so that is not correct. I have to use this. So if I plug in for every 1 mole, I have 180.2 grams. Okay, it doesn't matter if this is a larger compound. When you add up those masses, it's always based on 1 mole. So that's what's unique about our periodic table and the system that we use. Okay, and so moles of aspirin. Okay, and so units cancel. We're left with moles, and that's what the problem asked for. So here it is, what we just did, and we get 0.555 moles of aspirin. Okay, if you're converting to moles, you're always going to get a smaller number than what you started with. So if you accidentally plug this in wrong, kind of use common sense to help you. Okay, if my number's too big, my number is bigger, that means that I multiplied instead of divided, because to get your answer here, you would take 100 divided by 180.2. You have 3 sig figs, so your answer is reported to 3 significant digits. Okay, a practice problem. How many moles are contained in 60 grams of ozone? So I write out what I'm given, and we're going to go ahead and write the compound as well. This is going to help us later when things get more complicated. Okay, because not only does my unit have to cancel grams, but I have to be dealing with the same compound. So O3 also has to cancel. All right, so first thing I've got to do is I've got to think about how I'm going to get to moles. Okay, so to get from grams to moles, I'm going to use the molar mass. Okay, so I have 3 oxygens. So this is a pretty easy one. So oxygen has a molar mass of 16. You have 3. So 48 is your molar mass. Okay, whenever you use the periodic table, so I should have said this earlier over and over, but whenever you go to the periodic table and you add up the molar mass or add up anything from the periodic table with respect to its atomic weight, then it is always out of 1 mole. So far, every time we've plugged in mole, it's been 1 as far as in our conversion factor. Okay, and so 1 mole goes here. Okay, some students see that this is a compound or it's a larger number here and they want to try to make it more moles. Okay, the common unit here and the common thing going on is we have 1 mole. Okay, we have 48 grams of ozone for every 1 mole because we went to the periodic table and we added that up, and so I believe that should give us 1.25 grams cancel, and don't forget your units. We have 1.25 moles of oxygen. Okay, we can do this in reverse, so I just want to show this just in case you come across this, but our general sequence is we go to grams to moles and then we continue on with that, and we'll do that in later lectures. But if we were, for example, wanting to go from moles to grams, so the reverse, you're going to use molar mass. Here we divided, right? If you look up here, we divided 60 by 48, you get 1.25. If you do the reverse, you're going to multiply. So we're just going to pretend that we're in the problem. We were told we have 1.25 moles of ozone and we want to convert to grams. So we're going to get the same answer that's up there, but just for practice purposes. So if we were given moles, then that means mole has to be in the denominator here. So moles will cancel. So in every 1 mole of ozone, we have 48 grams of it. And so this time we multiply. So when you multiply that 1.25 times 48, you get 60 grams. Okay, so all I wanted to show you was how you would do this in reverse, and so I just did the reverse of this problem here. Okay, but if you start with moles and you go to grams, you're going to you're going to multiply times the molar mass. All right, I hope this helps. Thank you.